All right, so this is section 8.3, Applications in Physics and Engineering. So this section and the following section is just applications of what we can, what we've done so far, in everyday life. So this was just the physics and engineering. The other one is the natural sciences and stuff like that. But we're just going to go through the section when it comes to it. I'm going to nitpick each one individually when it comes to it. So this section has a couple things corresponding to it. Different types of scenarios you're doing engineering and physics. And I think there's a total of 3 of them. We're just going to be doing one, and that's going to call the central mass itself. Okay. So if you're wondering, that's why it's a pretty short section as well. Okay. So in this section, we're going to talk about the center of mass of a region. So if you're wondering what in the world does it mean to have a center of mass? Okay. Kind of think like a circle, right? That's like the center of the mass of a circle. It's exactly in the center. That's what we're talking about here. So again, the best way to also think of it is like a seesaw. So if you guys ever done on a seesaw, if you guys are younger, right, 2 people here and here, and what you really want to do is figure out at what point is this completely balanced, right? So it's like leveled when it comes to it. That's what it means by the center of mass when it comes to it. Okay. So in geometry, going back a little bit, so if we have a circle, right, its center mass is exactly in the center, or the center of the circle, right, with the radius r. Now, what we want to do is figure out what this point actually is, because that's our whole point. Is what's the point that it's the exact center of this region or this solid itself, et cetera, et cetera. So if we do this, right, we know that if I go straight down here, that's x naught. Okay? So we know the x value of our, x comma y coordinate pair is going to be some x naught that's exactly in the center. Okay? And therefore, f of x is going to be the radius itself. Right? Or if you want to go this way, it really doesn't matter. It's going to be f of x, some value that's on the actual circle itself. Okay. Now, when it comes to it, since the radius is half of the diameter, we know that the y value is always going to equal to 1/2 of f of x itself. And that's in general when it comes to a general circle, okay, right, to find the actual value. So now if we translate it to an actual region where we have curves, so for example, if we bounded between here and there, right? We need to figure out at what point somewhere on here is the actual center of the whole thing. Okay? And now how we do this is the same thing as when it comes always like random sum. So I know for a fact that there is some rectangle that has the center of mass, right? That has that particular point on it. So somewhere in the interior or very, very close to the actual line. Okay? And again, that point is going to be some value of xi, right? Somewhere over here. And also translate to the y value of also 1/2 f of xi, right? If we just plug in that initial value, just like we did over here. Okay? So in general, right? So the general format is how to find the center of mass of a region, or a centroid, the fancier way of terming it, is given by the region of x bar, y bar, so that's the center we're looking for, and each one has its own particular equation, where the x component is equal to 1 over the area of the integral from x times f of x dx. And again, this is going to be tough because we have to find the area of this region now, so it could be a little tricky. And then the y value, or x bar, is going to equal to 1 over the area times, again, notice, the 1/2 of f of x squared. Okay? So those are how we're going to find the center of mass of any object or any solid we're going to be generating. And again, since we're simply just in the second part of calculus, we're not going to be doing solids, but you would do the same thing when it comes to it. So you guys will be doing that later on in the course in multivariable calculus. But for now, we're just going to do a basic region, so the area itself, right? So no rotations or revolutions about anything when it comes to that kind of stuff. Okay? All right. So it's going to be a little lengthy because the area is going to be the hardest part to figure out how to do. You'll find the area of this region bounded by that subportions. So meaning we have to go back to the very beginning of the semester to find areas between them. So are we going to subtracting, all that fun stuff using the disk, washer, or the shell method, right? Hopefully not the shell method, right, when it comes to them. So let's try an example so you can see how this would come into play. So find the center of mass of a region bounded by the curve y equals, and this is supposed to say y equals the square root of x, y equals 0, and x equals 1. Okay. So why don't we just quickly draw what this is. So it's a square root of x, so we know essentially it does this, right? So 0 and 1, 1, and it does that. So what is our area we're looking for? So it's between y equals 0 and x equals 1. So it's this region right here is what we're looking at. So we need to find the exact center of that region there. So it's kind of like a curved triangle. Okay. All right, so now we know what we're dealing with. And the area is easy because finding the area is just basically just finding the integral, which is a good thing. So the area of a region is just the integral of the square root of x from 0 to 1, which is the best part. So taking the integral, this is x to the 1/2, so this is x to the 3/2 times 2/3, evaluated at 0 and 1. And here, plug in 0, that goes away, so plug in 1. So we know our area is equal to 2/3. Okay. So now that we have that, now let's go back and find x and y respectively, right? Each expected point itself. So x bar is equal to 1 over this, or essentially 3/2 now, integral from 0 to 1 of x, so literally the word, x itself, times our original function there, dx. Okay. Now, you may be thinking this is kind of weird, right? How do we evaluate this portion itself? And again, like everything else, is just a little trick when it comes to it. And that trick is actually putting these two together. So another way to write this value, again, using exponent rules, is x to the first times x to the 1/2, right? So remember when you multiply with the same bases, you add the powers themselves together. So this is essentially equal to x to the 3/2 dx. Okay. Or 1 and 1/2 gives you 3/2, right? And then notice it's not that bad of an integration, right? So take the integral again, so add 1, so this is x to the 5/2, 2 to the 5th, evaluated 0, 1 times 3 over 2. Again, right, 1 is the only thing that really matters, so we plug in 1, we get 2/5 times 3 over 2, 2's cancel, and we get the x component is going to be 3 over 5. Okay. So x is roughly 3/5, so about right there. And now we got to figure out how high we're going to go to find the center of mass there. Okay. Now for that, we're just going to use roughly the same situation as we have here now. So now the y component is going to equal to 1 over a, so again, it's just 3/2 times integral of 1/2, so I'm just going to pop it out here to make it easier for myself. Again, from 0 to 1 of the function squared. So it's a square root of x squared. And, notice that's actually pretty nice because those cancel. So we just get 3 over 4 integral of 0 to 0 of simply x. Okay. So this integral is just x squared over 2, evaluated at 0, 1 times 3/4. Again, 1 is the only thing that matters. So 1/2 times 3/4 gives you, 3 over 8. Right? So our point is 3 over 5, 3/8. Okay? So again, it's going to be roughly estimate. Let's here, approximately there is our center of mass. So if I would literally balance that on, let's say, like a pen, right? If I put balance that, if I could literally cut this out, and at that particular point, it would be completely balanced, right? Hence why it's called the center of mass itself, which is a pretty cool concept, right? When it comes to, so you could find the center of mass of any region we actually could create itself. Okay. Right? So not too bad, right? When it comes to it. So the good thing is, right, we can also do with two curves. Same thing, right? What it means by it. So like I said, we're going to either have to use a disk, washer, or shell method, which is, the horrible ones when it comes to, the centroids have two curves themselves. Okay, so this is the easy one where it's just one curve, right, bounded between lines, so that's not too bad. But again, we have all had areas between two curves now, so we can also do the same thing, applies this one. And it's pretty much the same process, right? It just f of x minus g of x, top minus bottom, essentially, when it comes to it. The only thing you got to be careful of is f of x squared minus g of x squared. So it's not like x minus g all squared. So just be careful of this portion here. But everything else is pretty much the same concept there. Okay. So let's try an example so we can see how this is going to come into play. Okay. All right. So we want to find the centroid. So again, the centroid is essentially the same center mass. The region bounded by the curves y equals x minus 2 and y equals x. Oh, x squared. So it's supposed to be x squared. X minus 2 squared and x. All right. So again, just like last time, we'll just do a quick little sketch and see what's actually going on. What's our region we're going to be graphing itself.